Here we will be examining the HP3588A spectrum analyzer. In this clip we will be looking at repairing a unit that has suddenly failed to self-calibrate. Let's fire up the unit. As normal, the unit automatically performs a calibration post-startup. We can see the calibration failure displayed. We bring up the hidden service menu. Hit special function. Second last soft key. -99. Second last soft key. Hit service functions. Self-test. Long confidence test. These tests will take a few minutes. We note a few failures along the way. We note the quick confidence test has failed. Hit special function. Service functions. Self-test. Test log. We note the post divider fails. Receiver auto range fails. Receiver second intermediate frequency fails. Receiver digital converter fails. Hit next page. We have a bunch more failures. So, where to from here? Open Operating and Service Manual. Go to Service. Troubleshooting with self-tests. Note point 7. If you have multiple failures as we do, we must use the order of table 5-12 when fault finding. Go to 5-12. We note the first failure is the second intermediate frequency. Probable faulty assemblies are the A61IF, followed by the A11 input. The suggested test to perform is test 18, input conversion. Go down to 5-52. Test 18, input conversion. Says to use this test if all prior self-tests have passed. This looks like it matches our case. We note the input conversion block diagram. Input A11 is routed to first conversion A12 and then to second conversion A13. Let's perform this test. We will make do with an oscilloscope for measurement within the signal path. Start your signal generator, let it warm up. Set the frequency to 10 MHz. Set the amplitude to -20 dBm. Plug your generator into the analyze's input. Hit preset. Special function. Auto cal off. Range input. Range. Enter -20 dBm. Sweep. Manual. Set the manual frequency to 10 MHz. As per table 5-19. Place a jumper from the A11 board J3 into your oscilloscope. You may or may not see the 10 MHz waveform on the oscilloscope. In our case, we see the waveform. Whether or not you see the waveform, we want to run a calibration during this monitoring. We have noticed an anomaly after performing a calibration. Do the following. Hit special function. Single calibration. The waveform will disappear as the self-test inserts its own signal into the input. At the end of the calibration, the self-test should restore the generator's signal and you should see the waveform on the oscilloscope. In our case, the signal is absent. Try this a few times. Give the A11 assembly a light tap on top with the handle of a small screwdriver. We see the signal restored on the scope. Why? Our hunch is something mechanical. One of the many relays in the input assembly is failing. By lightly tapping the assembly, the contacts can release or bed properly. Let's take a look at the input assembly more closely. Open the component level information packet set manual. Go to A11 input assembly. Go to A11 schematic. We note a number of relays in the input switching. These feed into the input attenuators. K103B, K104B, and K105B. One of the most common failures of many spectrum analyzers and oscilloscopes is the failure of attenuator relays. Quite simply, they are the most used relay and wear out. They can either stick in position and or not make full contact on one or more poles. We will start checking these relays and see where that takes us. Scroll back up to the component locator. We note the location of K103, K104, and K105. Let's pull the A11 assembly for a closer look. Disconnect J1, 2 and 3. Remove the two retaining screws. Grab the handle and slowly but forcefully remove the assembly. Remove the shields from the input attenuators. Remove the 6 screws from the shields. Remove the shields and set aside. A close-up of the 3 attenuator relays. We will put the A11 into a riser and test in circuit. Place a patch cable on J4. This is the input connector. Connect the other end into our signal generator as used earlier. We will use a riser on J5. I will leave details of where to obtain these risers in the comments. Insert the riser into the main board. Insert the edge risers into the board slots. These risers allow access to J4 in circuit. Place the A11 into position. Replace the small patch cables from J1 and J2 with longer ones. Reconnect the oscilloscope to J3. Set the unit up as we did earlier. Hit preset. Special function. Auto cal off. Range input. Range. Enter -20 dBm. Sweep. Manual. Set the manual frequency to 10 MHz. Note the 10 MHz signal on the scope. Perform a single calibration as before. Hit special function. Single calibration. After the calibration has completed, the signal is lost as we noted earlier. Place a probe onto channel 2 of the scope. Place a probe ground onto J4 ground. Let's trace the input signal through the attenuators as per the circuit diagram. Place the probe tip onto pin 11 of K103. We can see the 10 MHz signal. This tells us the input switching relays are probably okay. Place the probe tip onto pin 4 of K103. The signal is not present. This indicates a problem. Whilst holding the probe on pin 4, lightly tap the assembly around K103. We can see the signal is now on pin 4. Although we still do not have an output on J3. Place the probe tip onto pin 4 of K104. No signal. Lightly tap the assembly around K104. We now have an output on J3. Place the probe tip onto pin 4 of K104. We now have the signal. We have our smoking gun. Both K103 and K104 are faulty, and probably K105. Let's pull K103 from the board. Due to the large ground plane around these relays, we must preheat the board to enable desoldering. With a reflow heat gun, slowly bring the board up to around 100 degrees Celsius. Once up to temperature, use the heat gun by hand and closer to each pin to desolder. Once you are satisfied you have removed most of the solder from the joints. Grab the relay from the bottom of the board with both thumbs and forefingers and forcefully twist the relay left and right. Whilst difficult and time-consuming, with a little patience the relay will come free. Finally out we note the full part number, RG2ET-12V-H11. Let's look this up. I have an old Aramat reference manual. We know it's an RG-type relay. Go to page 16. The ET tells us it has a characteristic impedance of 50 ohms. The 2 tells us it's a 2-form C-type, 2 poles, 2 throws. The 12V tells us it has a 12 volts coil. It's non-latching. Single-side stable. Looking at the diagram, we note pins 2, 3, 5, 6, 9, 10, 12 and 13 are connected to ground. This is normal for a high-frequency relay with a specified characteristic impedance. Unfortunately, I cannot see any information regarding the H11, and nothing online either. This may be a special part for HP. We will need to check it out further. Let's put this relay under test. We have the relay coil pins 15 and 16 hooked up to a power supply with a suitable back EMF suppression. The center pin of each pole, pins 4 and 11, are connected to DMM positive. The green clip is connected to the DMM ground. The green clip is on pin 1. With the power off, we have a resistance of 0.1 ohms across pins 1 and 4. Pin 1 should be the normally open pin, but clearly this is closed. When we apply 11.4 volts to the coil, the pole opens on pins 1 and 4 and we see high impedance. This does not match our standard relay, as pins 1 and 4 should be closed under power. Let's continue the test. Remove the power. Note the resistance on pins 1 and 4 is now around 3 ohms. Clearly this relay is sick. We give it a light tap. The resistance drops to 0.1 ohms. We move the green clip to pin 7. Pin 7 should be the normally closed pin, but clearly this is open. Apply power, the pole closes on pins 4 and 7 and we see around 5 ohms. We give it a light tap. The resistance drops to 0.6 ohms. Again sick. Clearly this is not a standard RG relay layout, the normally open and closed pins are reversed. We tested the second pole with similar results. We will need to find a suitable replacement for these relays. This is the schematic we have come up with for the RG2ET-12V-H11. When compared to the standard RG2ET, you can see the first pole reverses the normally open with the normally closed pins. Let's consider a substitute for the Aramat relay. It's worth noting that Aramat was part of Matsushita Electric Works, and was renamed to Panasonic Electric Works back in 2005. This is relevant as we have chosen the Panasonic Electric Works ARA200A12 relay as the replacement. Matching or beating the Aramat in almost every specification, the important specs are: characteristic impedance, frequency, voltage standing wave ratio, insertion loss. This is important. Isolation is one area the Aramat beats our substitute. This won't be an issue for our purpose. Contact resistance, switching voltage, switching current, operate and release times, much faster. Expected life is much greater. Let's compare the coil specs. Nominal coil voltage. Pickup voltage, less is fine. Coil resistance, higher is okay. Nominal power, reduced power is fine also. So we have found what looks like a very good substitute. However, the obvious issue is how we physically replace the through-hole relay with a much smaller surface mount relay. We have designed an adapter board. We call this the RG adapter. This board has been designed to maintain a 50 ohm coplanar characteristic impedance. The pinout will match our RG2ET-12V-H11 exactly, and will mount in its place. Let us know in the comments if you are interested in how we designed and tested this board. Details on obtaining the board are also available in the comments. Let's mount the ARA200A12 to the adapter board. Clean the board with isopropyl alcohol. Apply no clean flux to the surface pads. Solder one of the relay can ground pads. Keep the relay leads aligned. Solder the diagonally opposite pad. Again, ensure all relay leads are aligned. Solder the other two can ground pads. Proceed to solder the remaining pads. Tin the coil pads in preparation for the leads. Solder the coil leads made of AWG22 copper-tinned wire onto each of the coil pads. Place a 20 mm length of heat shrink onto each of the coil leads. Bend each of the leads into the respective coil pad. Note the polarity marked on the board. Apply a heat gun to shrink the heat shrink. Ensure to protect the relay with a metal shield. Place the adapter board into position. Insert short lengths of AWG22 copper-tinned wire into pins 1, 7, 8 and 14. Pins 4, 11, 6 and 13, the latter being ground. Note it is not necessary to solder all the ground pins. Solder these in place. Turn the board over. Solder to the board. Ensure the adapter board is sitting flat against the A11 board. Although not shown in this clip, we recommend removing and installing all three relays at once to avoid reheating the board. Trim leads from both sides of the board. Remove the redundant ground leads we used to help alignment. Here is a picture of the board with the upgraded attenuator relays, K103, K104 and K105. Insert the board in the unit ready for testing. With the board installed, start up the unit. As usual, the unit does a self-calibration on startup. That's a great start. The unit has passed the quick confidence test. Let's perform a full test as before. Hit special function. Second last soft key. -99. Second last soft key. Hit service functions. Self-test. Long confidence test. These tests will take a few minutes. Hit special function. Service functions. Self-test. Test log. Next page. All tests have now passed. Let's perform a few basic tests on the unit's attenuators. Set the center frequency to 10 kHz. This is to test the lower frequencies on the unit. Hit the marker function. Set peak tracking to on. Hit frequency. Span. Set to 100 kHz. With our signal generator set to 10 kHz and 0 dBm. Plug the generator into the input. We see the auto range kicking in. The unit has detected the 10 kHz signal at 0.25 dBm, not bad. Set the signal generator to -20 dBm. The unit has detected the signal at -19.68 dBm, again not bad. Set the signal generator to +10 dBm. The unit has detected the signal at 10.25 dBm. Let's check the upper range. Unplug the signal. Hit center. Set the center frequency to 140 MHz. Set the signal generator to 0 dBm. The frequency to 140 MHz. Plug the generator into the input. The auto range kicks in. The unit has detected the 140 MHz signal at 0.08 dBm, pretty good. Set the signal generator to -20 dBm. The unit has detected the signal at -20.03 dBm, again that's pretty good. Set the signal generator to 10 dBm. The unit has detected the signal at 10.08 dBm. So that's about it. Really satisfied with the result. In the following clips we will cover more testing and adjustment of other components in the unit. This completes the clip. I hope you found it informative. Thank you for watching. Please subscribe, like and comment. Your feedback is important.